August 15, 1914. Ships waited on either side of a canal that cut across the Isthmus of Panama, their captains anxious and governments watching with bated breath. For centuries, merchants, engineers, and empires had dreamed of connecting the Atlantic and Pacific, imagining the reduction of thousands of miles of treacherous navigation around Cape Horn. But this dream demanded more than imagination. It demanded mastery over one of the harshest environments on Earth. Panama was a land of rivers that swelled without warning, of dense jungles that hid deadly diseases, of rainfall so relentless it seemed to carve the mountains into mud each day. Early French attempts under Ferdinand de Lesseps had failed spectacularly. Tens of thousands of workers succumbed to yellow fever and malaria. Bridges, dredges, and canals collapsed under landslides and floods. The project became a symbol of human ambition confronting nature's fury and failing. When the United States took over in 1904, the task seemed no less daunting. Engineers confronted swamps filled with mosquitoes, rivers prone to catastrophic surges, and a mountain range that seemed impassable without tunneling and locks. Every step required precise calculation. Unlike Lesseps' sea-level canal concept, U.S. engineers realized the solution lay not in brute excavation alone, but in engineering mastery. They would build locks to lift ships across the Continental Divide, controlled by steel gates, hydraulic valves, and gravity-fed reservoirs. The work was not just construction, it was a contest against water, time, and human frailty. Colonel George Washington Goethals assumed command of the Panama Canal project in 1907, bringing with him not only military discipline, but an engineering philosophy that would define the canal's unprecedented success. For Goethals, every detail mattered. Every rivet, every cubic yard of concrete, every steel gate was subject to scrutiny so meticulous that outsiders often dismissed it as obsession. To him, the canal was more than a construction project. It was a living machine, a complex organism in which every component had to function in perfect harmony. One small failure in any system could cascade into catastrophic delays, financial loss, or worse, loss of life. Under his leadership, thousands of engineers, laborers, chemists, and surveyors transformed an unforgiving landscape of jungle, swamp, and volcanic soil into a feat of enduring human ingenuity. Concrete was never poured blindly. Laboratory tests determined the exact mix to ensure compressive strength, durability under tropical heat, and resistance to relentless humidity and seasonal downpours. Steel, forged for the canal's massive locks, was measured and treated to exact specifications, each ton capable of withstanding pressures far beyond what any ship could exert. Goethals recognized that mistakes in these foundational elements would not simply cause setbacks. They could imperil vessels, destroy infrastructure, and ruin the lives of those who depended on the canal's success. Hydraulic valves designed to control millions of gallons of water were engineered with near-perfect timing. Each lock chamber, the heart of the canal, could lift ships up to 85 feet above sea level, guiding them through narrow concrete corridors with a precision that demanded flawless engineering and impeccable coordination. Water flowed in carefully calculated increments, filling and emptying each chamber so smoothly that massive steel gates, some weighing over 7,000 tons, moved without strain. These gates were designed not merely to function, they were built to endure storms, tropical heat, seismic activity, and decades of continuous use. The system was simultaneously massive in scale and precise in execution, a combination rarely seen in human construction. The marvel of the Panama Canal was not confined to the size of its locks or the sheer volume of excavation. Its genius lay in the integration of every system into a cohesive whole. Dams, spillways, locks, and channels were interdependent, each relying on the other to maintain water flow, control flooding, and guarantee operational efficiency. Goethals envisioned a canal that would not only accommodate the largest ships of the early 20th century, but function reliably under extreme tropical weather, a setting where lesser designs would have quickly failed. Every engineering decision, from the composition of concrete to the placement of a lock-gate hinge, reflected a philosophy that valued permanence, resilience, and scientific rigor above expedience or cost-cutting. Goethals demanded a level of scientific precision that was revolutionary for his time. Engineers conducted extensive calculations for water displacement, lock pressures, and flow rates. Chemists tested steel and concrete repeatedly, ensuring each batch met stringent quality standards. Surveyors mapped the terrain in extraordinary detail, accounting for the shifting soil, underground water channels, and seasonal fluctuations in the Chagres River. No variable was too small, no assumption untested. Goethals understood that the canal's success would not be measured by the speed of its construction, but by its reliability for generations of ships yet to come. In every sense, the Panama Canal was a triumph of methodical planning and meticulous execution. It reflected the brilliance of Goethals and his team, whose insistence on precision, integration, and oversight created infrastructure that would endure far longer than contemporary projects built with modern technology. The canal's locks were more than mechanical devices. They were a testament to the philosophy that careful design, rigorous testing, and human skill could conquer nature's unpredictability and deliver a structure of lasting excellence. Panama's climate threatened to undo every calculation. The Chagres River, notorious for flooding, could rise 30 feet in a single day. Engineers constructed the Gatun Dam, creating Gatun Lake, which would supply the canal with water and control river flows. The lake itself became a reservoir of both transportation and engineering ingenuity. Every dam, lock, and channel was designed with overflow, safety margins, and redundancy. When water levels rose, the locks could compensate without risking structural integrity. Unlike modern upgrades that focus on automation or speed, the 1914 design prioritized resilience. The engineers understood the value of tolerances, over-engineering, and planning for the unknown. Disease control was another critical factor. Thousands of workers would not survive the project unless malaria and yellow fever were eradicated. The engineers collaborated with medical experts to drain swamps, fumigate construction zones, and isolate outbreaks. The combination of engineering and public health strategy ensured that the canal could be completed and operated sustainably. By 1914, the canal was more than a passageway. It was a triumph of foresight, a structure that married nature, science, and human ingenuity. Its gates and locks reflected a deep understanding of hydrodynamics, material science, and large-scale logistics. It was, in every sense, engineered for permanence. Opening day arrived, and the Panama Canal functioned with a precision that seemed almost miraculous. The first ship to pass through its locks, the cargo vessel SS Ancon, moved steadily from the Atlantic to the Pacific, guided by gates and chambers that had been meticulously calibrated over years of construction. Engineers, politicians, and laborers held their breath as the massive steel and concrete machinery performed flawlessly, each lock filling and emptying with exacting accuracy. For a moment, skepticism melted away, replaced by awe at what human ingenuity had carved through jungle and rock. Yet the true test of the canal's design would not be completed in a single day. Ships grew larger, cargo loads heavier, and global trade expanded far beyond what the original planners could have imagined. Decades passed, and through wars, economic booms, and shifts in maritime technology, the original locks continued to function without systemic failure. Steel gates, massive concrete walls, and the hydraulic principles perfected under the supervision of George W. Goethals and his team proved remarkably resilient. The structures expanded and contracted with temperature, endured tropical storms and relentless humidity, and resisted wear from the constant passage of vessels, all without the need for fundamental redesign. By contrast, modern upgrades to the canal have struggled to replicate this reliability. The 21st century expansion, designed to accommodate Panamax and post-Panamax ships, brought with it complex automation, new hydraulic systems, and cutting-edge control software. Yet these systems introduced vulnerabilities the original engineers never faced. Automated gates malfunctioned, sometimes failing to respond correctly to commands. Sensors required constant recalibration, and the sophisticated computer-controlled mechanisms, while impressive on paper, created points of failure that did not exist in the purely mechanical, human-operated locks of 1914. The lessons were clear. Complexity can create fragility, and untested innovations, even with modern technology, cannot always outperform a system built on simplicity, precision, and over-engineering. The secret to the canal's enduring reliability lies in the philosophy of its original design. Goethals and his engineers anticipated every conceivable challenge and overbuilt critical components far beyond the minimum necessary. Each steel girder, each concrete wall, each lock gate was sized to withstand loads, stresses, and pressures far exceeding what normal operations would demand. Redundancy was not an afterthought. It was embedded into the very DNA of the canal. Backup systems, secondary valves, multiple safety features, and generous structural margins ensured that even if one component failed, the system as a whole would continue to operate. Extreme scenarios, earthquakes, unprecedented floods, surges in traffic, were not just considered. They dictated the specifications of every major component. This approach stands in stark contrast to many modern engineering projects which often prioritize speed, cost efficiency, or optimize capacity over long-term durability. While the 21st century locks can handle larger ships, their margins for error are tighter, their components designed closer to theoretical limits, and their reliance on technology creates points of potential failure that never existed in the original system. The 1914 canal demonstrates that over-engineering, when applied intelligently, does not waste resources. It ensures longevity, reliability, and adaptability that modern shortcuts cannot replicate. Even as the Panama Canal continues to expand and modernize, the original locks remain a benchmark of performance. Engineers study them not only for their historical significance, but for the enduring principles they embody. Anticipate challenges, design for extremes, test rigorously, and never compromise on quality. The SS Ancon's inaugural passage may have been the first public display of the canal's brilliance, but every ship that has traversed its waters since is proof of an engineering philosophy that has stood the test of time. Over a century later, the locks continue to function with remarkable reliability. A silent reminder that true durability is built on foresight, precision, and the willingness to design not for the moment, but for generations to come. The longevity of the Panama Canal owes as much to the materials chosen as it does to the hands that shaped them. From the beginning, engineers understood that tropical heat, relentless humidity, and the chemical composition of river water would quickly destroy anything built without foresight. Concrete for the locks was not ordinary. It was a carefully engineered mixture that included volcanic ash, producing hydraulic cement capable of setting and curing underwater while resisting chemical erosion over decades. Each cubic yard was tested for compressive strength and durability, ensuring that walls and chambers would withstand the immense pressure of millions of gallons of water lifting and lowering ships day after day. Steel gates, the very teeth of the canal, were fabricated with tolerances so precise that each segment fit seamlessly into the lock chambers. Massive pins and hinges were machined to exact dimensions, ensuring smooth operation despite continuous exposure to water, weather, and mechanical stress. Even after a century, these gates move with the same fluidity as when they were first installed. Every beam, bolt, and bearing was chosen and assembled to create not just a functional lock, but a system that could endure for generations with minimal maintenance. But materials alone could not achieve such extraordinary reliability. Every piece of machinery underwent rigorous testing before it became part of the canal. The culverts that filled and emptied lock chambers were measured and adjusted to guarantee precise water flow, preventing turbulence that could unbalance ships or damage the gates. The locomotives, affectionately called mules, guided vessels through the locks, absorbing forces that could otherwise strain hulls or compromise alignment. These small yet powerful machines required operators with acute judgment, ensuring ships moved safely through narrow chambers with astonishing precision. No modern automation, no matter how sophisticated, could replicate the subtle responsiveness of these human-guided operations. The human factor was central to the canal's enduring success. Engineers, laborers, and technicians worked with a sense of personal ownership that elevated quality beyond written specifications. When unexpected challenges arose, shifting soils, sudden floods, or minor misalignments, workers improvised solutions on site, blending scientific knowledge with hands-on ingenuity. Each decision was informed by decades of observation, experimentation, and the practical wisdom that comes only from building and maintaining infrastructure in real conditions. The lessons embedded in these experiences cannot be encoded into software or prefabricated components. The combination of material excellence and human craftsmanship created a self-reinforcing system. Superior concrete and steel made the locks resilient, but it was the careful installation, continual oversight, and expert judgment of generations of canal workers that allowed them to function flawlessly. Modern contractors often rely heavily on simulations, prefabrication, and remote monitoring, yet these methods can overlook subtle real-world variables, minute expansions of steel, minor shifts in foundations, or water behaviors that only reveal themselves under prolonged, repeated use. Goethals understood that mastery of the tangible world, materials, machines, and human skill would always outperform designs dependent solely on theory or technology. The Panama Canal is a monument not only to engineering genius, but to the philosophy that quality is inseparable from those who shape it. Every gate, every lock, every inch of concrete carries the imprint of human attention, precision, and care. It is a living demonstration that when material excellence meets human craftsmanship, infrastructure can endure far beyond expectations, outperforming even the most advanced modern upgrades that lack this same depth of hands-on wisdom. As the canal approached its centennial, engineers observed something remarkable. The original 1914 locks operated with minimal maintenance, while modern expansions required frequent calibration, replacement of mechanical systems, and extensive monitoring. Scholars and engineers studying the canal found that the original construction philosophy, emphasizing over-engineering, redundancy, and meticulous control of materials, produced durability that modern cost-cutting often sacrifices. The contrast is stark. Today, global infrastructure projects are frequently optimized for speed and profit margins rather than long-term performance. New bridges, tunnels, and canals may appear more sophisticated, but their systems are complex, less forgiving, and dependent on technology that can fail. In Panama, the genius of 1914 persists not because it was cheap or fast, but because it was deliberate, redundant, and human-focused. Today, over a century later, the Panama Canal stands not just as a passage between oceans, but as a living monument to human ingenuity and foresight. Its original locks, constructed in 1914 with meticulous care, continue to operate with remarkable reliability, guiding tens of thousands of ships across the isthmus each year. These locks, engineered to withstand the heaviest vessels of their time, have adapted gracefully to the evolving demands of global trade, while many modern expansions, despite cutting-edge technology, grapple with teething problems, mechanical malfunctions, and the challenges of untested systems. The lessons are unmistakable. True engineering excellence is not measured by speed, novelty, or automation alone, but by permanence, precision, and foresight. The Panama Canal demonstrates that when every component is designed with exacting standards, when materials, mechanisms, and human skill are harmonized, the results endure far beyond initial projections. Every lock gate, every sluice, every massive chamber tells a story of calculation, experimentation, and painstaking care. These structures were conceived to resist not only the pressures of water and weight, but the wear of time itself. The canal is more than steel and concrete. It is a chronicle of human determination. Engineers of 1914 understood that the forces of nature, the sudden torrents of the Chagres River, the tropical heat, the constant rainfall, could undo lesser projects in months or even weeks. Their solution was an integrated system that married hydraulic science with human oversight, where each valve, each culvert, and each lock operated in concert with the others. Redundancy was built into the design. Tolerances were generous, and the workman's skill ensured that even the smallest error could be corrected before it became catastrophic. Modern upgrades, by contrast, often rely heavily on software controls, automated systems, and modular construction. While these innovations bring efficiency, they cannot replace the kind of systemic foresight and hands-on craftsmanship embedded in the original locks. The impact of this durability is profound. Ships today glide through the locks with the same reliability as those that crossed 100 years ago. Freight schedules remain predictable, maintenance costs remain manageable, and the canal continues to facilitate global commerce without the dramatic failures that plague many contemporary infrastructure projects. Its continued operation is a testament to the value of designing for permanence, rather than temporary convenience. Beyond the technical triumph, the canal offers a philosophical lesson. It reminds engineers, planners, and policymakers that shortcuts, cost-cutting, and over-reliance on technology often compromise longevity. In contrast, careful observation, rigorous testing, and a commitment to enduring quality can yield structures that serve not just a generation, but multiple generations. The Panama Canal embodies a mindset that sees infrastructure as a legacy, not merely an expense. As the 21st century progresses and ships grow larger, new lanes and modern locks are added to increase capacity. Yet the shadow of the original 1914 construction looms large, a standard against which all upgrades are measured. Even as technology evolves, the principles that guided Goethals and his team remain relevant. Anticipate challenges, integrate systems with precision, respect the materials and forces at play, and never sacrifice quality for expedience. In every sense, the Panama Canal is a monument to timeless engineering. It endures not because it was the fastest or cheapest project of its era, but because it was conceived with permanence, intelligence, and human skill at its core. It is a living demonstration that the best engineering transcends time, proving that foresight, craftsmanship, and resilience often outperform the newest tools, innovations, or automation. Over a century later, ships still glide through its locks as reliably as the first vessels did, navigating a pathway carved not only through the earth, but through history itself. The Panama Canal, a marvel of 1914, continues to teach the world that true engineering excellence is measured in decades, not months, and in generations, not mere years.